Hi all. This is the Wednesday lecture content. It will be split up in a couple of shorter videos to make it easier for you to view. First, the overarching theme that we're discussing is Cauchy sequences, completeness, and subsequences. I will divide this video into three parts. First, there is a discussion on the background that's related to going back to concepts from 131a. Second, there will be a video discussing the definitions and some examples related to them. And then finally, we will state some theorems and discuss their proofs. And some of those proofs also are part of the material for the Friday lecture. So let's go back to 131a. And we discussed some of these concepts, especially Cauchy sequences and subsequences already back then. And let's see some things that answer some questions that we had already in that class. So first a question, how to prove that a sequence converges without knowing what the limit is? Now, if you know what the limit is, you would apply an epsilon delta condition. You would estimate the distance, or sorry, epsilon n condition. You'd estimate the distance from xn to x, and then you try to make this less than epsilon by choosing an n sufficiently large. But if we don't know what the limit x is, then our tool mainly was Cauchy sequences. And we had a theorem that, well, a sequence converges if and only if it is Cauchy. And the definition of that was that for every epsilon, there exists an n such that if you're after that index, then the distance between them is at most epsilon. And really thinking of this absolute value xn minus m, xm, as a distance, that then allows us to extend this to a metric space setting. Now, some applications of how we use this and why this was important was in proving that an absolutely convergent sequence is also conditionally convergent. Indeed, the differences of the sequence of partial sums of the conditional sequence series can be bounded by the differences in the absolutely convergent series. And this gives us immediately this Cauchy sequence condition. Now, we would like to generalize this theorem to metric spaces, but we face some problematic examples, and these are the examples that you should think of when we're generalizing this to metric spaces. So first of all, our spaces can have somehow holes in them. And one example of this is if we take as metric space the half open interval 0 to 1, this is our space x. We take the usual metric x minus y. Then if our sequence is 1 over n, then well, xn is a sequence that converges in R, and because it converges in R, it's also Cauchy. But it does not converge in X because the limit point 0 is not in X. So somehow there's a hole corresponding to that. Now, you could have a lot more holes in your space, and Q is an example of that. If we take the rational numbers Q with the usual metric, then you can find a sequence of rational numbers that converges to pi, or any other irrational number, say square root 2. And this sequence is Cauchy because it converges in R, but it does not converge in Q because the limit point is not in there. So this is not in Q. That's the crucial point here. And you might remember actually another concept in 131A saying that about completeness, meaning that the soups always exist. And this is very much connected to the issue that Q is not complete. It does not satisfy this completeness axiom. So this is the issue that Cauchy sequences may fail to converge if there's some sort of holes in the space. Okay. Well, let's think of another question that goes back to our content from 131A. And I also recommend this in general with the concepts of this class. First, try to understand them in R, where they're usually reduced to things in basic theorems, and then try to extend them to other spaces and to understand how they behave. So the question here is, if I have a sequence of real numbers, then can I find a convergent subsequence, or when can I find such a convergent subsequence? And by a subsequence, what we mean is that you take only some of the elements, nk, indexed by some nk, where k to nk is an increasing function. Indeed, as k goes to infinity, nk goes to infinity. So what was the condition for this? Well, we had the main condition that we got is that the sequence is bounded. If xn is a sequence of bounded sequence of real numbers, BDD is an abbreviation to be bounded, then there exists a subsequence such that it converges. So, an application of this. This actually is more important than the Cauchy sequence result for many practical purposes. And this arises in optimization. It arises in finding minima and maxima of functions. And the problem is that, well, you want to find a minimizer for a function, or to even prove that this minimizer exists. And in 1D and ND and dimensions, we call this the extreme value theorem when it exists. Well, the general scheme of these proofs and algorithms that produce minimizers is to find some sequence xn such that the function values of f of xn converge to the minima infinitely. But then if we want to actually, we don't know that xn converges, so we want to apply Bolzano-Weierstrass, and usually the first step is proving that this sequence is somehow bounded. It doesn't go off to infinity. There is a secondary concern in some application that doesn't go to the boundary of omega, and this we'll discuss more next week. But but after we've discovered that it's bounded, and sometimes it fails, but hopefully when it succeeds, then the third consideration is to find a convergent subsequence. Now, with this convergent subsequence, we get a limit xnk converging to some x star, and we hope that this is a minimizer. But to find this x star, we need some sort of subsequential limit. And this is probably the biggest reason why to discuss this issue. Now, indeed, let's discuss problematic cases for when the limit may not exist. Well, the first issue is this issue with unbounded spaces. So even if we don't take the entire R, we could take the non-negative real numbers with the usual distance. Then if we take xn is equal to n, then there's no convergent subsequence. Now, so this is one of the issues. Now, another problematic example when there are no convergent subsequences is again this half-open interval, 0 to 1. And xn is equal to 1 over n. Then this sequence also does not have any convergent subsequences in x because the limit point of all of them would be 0, but 0 is not in the space. So 0 is not an x is the reason for these to fail to converge. So there could be some missing points. Indeed, we need Cauchy sequences to converge in order to find convergent subsequences. Now, a third example is it's more abstract and much more difficult to understand, but I'll describe the example and describe a little bit of an intuition of why I call this somehow the space as being too big. So if we take x equals r with a different metric, namely the discrete metric, and if we take xn is equal to 1 over n, then, well, the sequence xn does not converge anymore. It does not converge to 0. But not only that, but no subsequence xnk converges either. In fact, what we have is that if we take any pair of indices, n not equal to m, then the distance between them, these points, is 1. And this is a little hard to draw as a picture, but you could imagine somehow a giant loop here, right? And it cannot be represented completely in the plane, but these points just keep going on and on, but in such a way that the distance between any pair of them, and this picture doesn't do justice to this because it seems like some pairs here are further from each other, distance between any pair of these points is 1. So I drew some of these distances here, and the points just keep going on. And this is x1, this is x2, x3, x4, x5, x6, etc. So we have this infinite collection of points whose distance is always 1. And the point here is that no subsequence x and k can be Cauchy. So no subsequence converges. This is the hardest example, and we'll probably see this again in some ways. So there are some spaces that somehow have too much space in them. They fit too many points inside themselves with too large distance. Now, this does not happen in Rn. This issue does not happen in Rn, as we will see. Okay. So this does not happen in Rn. Indeed, you can show a lemma that if you have a sequence xn in this metric space R with the discrete metric, and it's crucial that you have a discrete metric, then xn converges if and only if there exists an n such that this sequence is actually constant after a certain index. So this will actually follow from a result in the next lecture. Okay, so that concludes this introductory part. The next video in the sequence will talk about the definitions that we just introduced.